So just super basic starting point here. Let's say that I had a function like sine of 3x squared minus tangent of 2x. And I wanted to take the derivative of that. First of all, a couple different notations for derivative. Writing that f prime is probably the one that we use the most often, but one that we see a lot show up in 17b is to think about that as df over dx or df dx. In terms of derivatives, you have to have those trig derivatives memorized. So the derivative of sine is cosine. And the extra piece to this is because I had something inside of the trig function, there's something in the argument, I have to multiply by the derivative of that piece as well. That's our chain rule part. So I'm going to multiply by the derivative of 3x squared or 6x. When we've got addition or subtraction between pieces, then that derivative rule says we just treat them separately and either add them together or subtract them. Well, the derivative of tangent is secant squared. And one of the things to remember here is that calculus never changes the argument of the trig function. Only trig identities can change what's inside. Calculus can't change what's inside. So if this was tangent of 2x, when I take the derivative, I've got secant squared of 2x. That piece doesn't go away. But again, I've got to remember that chain rule, and the derivative of 2x is 2. So as a quick run through of our trig derivatives here, if I take the derivative of, it'll take me longer to write these out than it would take you to just do them, but I do want to write out each of our derivatives for our trig functions. And I don't know how much time we'll spend with the co-trig functions, but they do show up. So we should make sure that we've got those in our memory also. And so my derivative of sine is cosine. My derivative of cosine of x is negative sine of x. The derivative of tangent is secant squared of x. Derivative of cosecant is negative. Anybody remember? You can type it in the chat. So I'm going to take parts of things that people put in there. So let me start here. The derivative of secant of x is secant of x times tangent of x. And cosecant looks almost like this, but it's the negative and the cos. So it's negative cosecant of x cotangent of x. And then our derivative of cotangent is negative cosecant squared x. The truth is that most of the time in the 17 series, we're really living with these three, but sometimes these show up, so it's just good to have them in your memory. Other 17a differentiation stuff that's going to show up a lot for us in 17b are those lovely log and exponential functions. Just to refresh our memory here, maybe I've got a function that looks like 2x e to the negative x cubed, and I want to find the derivative. I kind of put a bunch of things together in this problem. So first of all, if I look at the big function, I know that I have this exponential piece because I have a base where my variable is in the exponent. But the other thing that's going on is some invisible multiplication between the 2x and the e to the negative x cubed. And because of that invisible multiplication, I know when we take the derivative, I have to be careful to use the product rule. We're just gonna try again with the camera. So we're going to need to use the product rule here. So I've got 2x times this exponential piece. So the product rule says if I look at those two pieces, I'm going to take the derivative of the first piece and get 2, multiply that by the second piece, leaving it alone, plus leave the first piece alone and multiply that by the derivative of the second piece. And whenever we take the derivative of an exponential, we get exactly the same thing back times the derivative of the exponent. In this case, negative 3x squared. Now there's one little thing to remember about this. So I misspoke when I said for an exponential, we get the same thing back. That's true whenever our base is e. But what if I switched this up and instead of a base of e, I actually had a base of, I don't know, 5. So if I had some function that looked like y equals, I don't know, I'm going to be boring. 5 to the 3x power. And I come in here to take the derivative. And this time I'll write that derivative as dy dx. Because it's an exponential, I do get a copy of the same thing back. I get the 5e to the x back. That's actually one of the properties that defines an exponential. But in addition to that chain rule piece where I take the derivative of the 3x and I get 3, there is also another piece that I have to multiply by out here. And Juan helped us out already with the formula. So that extra piece we have to remember to multiply by is the natural log of 5. Technically, we could write that up here on this line also when our base was e. It's just that if we do, when I multiply by the natural log of e, the natural log of e is 1. So usually we don't write that part. So just keeping track of time, I do want to do one example taking the derivative of a log function, and then we're going to switch gears, flip it all up, rewire our brains to switch to finding antiderivatives and thinking about this process in reverse. Just pausing for a second in case there were questions in the chat. I'm not seeing anything, so. The function here, I've got natural log of t squared minus 9. There is also a suggestion in the chat that I'm going to try in a second. Thank you. Let's hope that's what it is. So if I take my derivative here, whenever I've got a natural log function, my derivative is going to look like 1 over all of that stuff times, chain rule says I need to multiply by the derivative of the inside. So the derivative of the inside part here would be 2t. Now, I've written this as 2 separate pieces, but we could also think about that derivative of a natural log as saying what goes on the top is the derivative of the argument of the ln, whatever's inside of those parentheses. And then the bottom is just exactly what is inside of those parentheses. These two are equivalent. If you didn't have web work homework last quarter, and maybe it's your first time doing web work, luckily that first homework assignment is going to walk you through some of the mechanics of web work. But for sure, this is one of those cases where to make sure that what you're typing in is correct in web work, this is an easier way to type it, because this, if I were putting it into web work, I could write as 2t divided by 2 options for the t squared. I still prefer the caret. Some people like the double star. But this is an easier way to type this thing into web work. I already mentioned this, but not in section 4.6, but a better table for antiderivatives is on page 345 of our textbook. And I'm pointing that out for 2 reasons. One, so 4.6 is like a start of antiderivatives, but we're actually going to build up like 2 or 3 weeks worth of practice and techniques for finding antiderivatives. So this is just our starting point. So if it feels unfamiliar, if it feels uncomfortable, just know that we will have more time to be practicing these antiderivatives, but some of the basic rules that are in this table on 345, it's really going to help you out in the long run if you get these memorized quickly. So that said, let's talk a little bit about antiderivatives. We have a couple of different notations for antiderivatives, and one of them is going to be this kind of S-shaped integration symbol. We're going to see that in chapter 5. It's not really popping up in chapter 4 for us yet in 4.6. So I'm not going to use it today, but maybe by Friday we'll be using that other notation. In terms of 4.6 stuff, we might be asked something like, find the general form of f of x if, and then we're going to be told something about the derivative. So maybe I'm going to be told something like f prime of x is equal to 6x minus 10x to the 4th plus cosine of x. So rather than telling me a function and asking for a derivative, this is giving me the derivative and we need to work backwards to get the function. Well, in general, when I'm looking at a polynomial, the way we take the derivative would be to take the exponent, multiply it down by the coefficient in front, subtract 1 from the exponent. And when we're taking antiderivatives, we're reversing that process. So if I look at that 6x, if I'm finding my function, I know this has an invisible exponent of 1. And reversing that derivative process means I need to add 1 to the exponent. And since when we're taking derivatives, we multiply the exponent by what's in front, 2 ways to think about this. I can now think, well, when I take this derivative, I have to get 6x. So 2 times what would give me 6? And the answer there is going to be 3. And that's fine, but it's a little bit time consuming. We kind of don't want to have to think through that each time. Right here, I'd say, okay, I'm going to add 1 to the exponent, so I'll have x to the 5th. And then 5 times what gives me 10? Well, the answer there is 2. But mechanically, we can get that 3 or that 2 by using division. So more generally, when we're thinking about these derivatives for some kind of polynomial, I'm going to get there by taking that original 6x, I'm going to add 1 to the exponent and divide by the new exponent. Or here, I'd add 1 to the exponent and divide by the new exponent. Same answers, just written in a slightly different form. Now, in terms of the trig stuff, you just have to get it memorized. I have no cure for that. So I just have to look at cosine and say, whose derivative is that? Well, sine of x, because when I take the derivative of sine of x, I get cosine back. And for the trig stuff, you just have to memorize it. Sorry. There's another piece to this, and that is hidden in this word general. So when we talk about the general form for our f of x or our antiderivative, there's a piece that we always need to be careful to put on the end. And that's because this is the derivative of this function, but this derivative, it is also the derivative of that function. And it's also the derivative of that function. And it's also the derivative of that function. So when we talk about that general form, we're going to finish finding our antiderivative and then make sure that we add to the ends plus a constant. This is going to be important when you're putting answers into web work. Some of the web work problems are coded such that you have to type the plus C to get the answer correct. And annoyingly, sometimes there's a difference between a capital C and a lowercase c. And we're just going to have to play around with that. Hopefully they've all been coded correctly to accept either the capital or lowercase version, but I have seen people go crazy sitting at a computer trying to figure out what's wrong with their answer. And it's really just having to switch from a lowercase c to a capital C. Okay, more fun with antiderivatives. If we can take antiderivatives of polynomials, then sometimes we're going to have to get clever and look at what we have and turn it into something that looks more like a polynomial, or generally looks like a number times x raised to a number. For example, if I started off with something like 3x squared minus 2x times x to the fourth plus, oh, I meant to put the parentheses over here, x to the fourth plus 1. Well, if I'm staring at this thing and thinking about those derivative rules and trying to ask myself, wait, whose derivative is that? Well, we have a derivative rule that involves multiplication. But if this were some kind of product rule, I'd have like 2 pieces with a plus in between. So this didn't come straight from a product rule, which means the only way that I know to come up with this antiderivative is to multiply it out and get an actual polynomial we can work with. So sometimes we have to do a little bit of algebra first before we can find that antiderivative. So I'm not finding the antiderivative yet, so I'm going to be careful about my notation and make sure it still says f prime. And then over here, I'm just going to FOIL it out or multiply it out. So I'll take my 3x squared, distribute that in. So 3x to the 6th plus 3x squared, and then take my negative 2x and distribute that in. So I'll have negative 2x to the 5th and minus 2x. Once I get to this point, now I can find that antiderivative by thinking about each of these as a number times x raised to a power. So when I take that antiderivative, I'm going to add 1 to the exponent and divide by the new exponent. Or to write that kind of generically, I could say if I have ax to the n and I take the antiderivative, I'll end up with ax to the n plus 1 divided by n plus 1. Doing that for each piece here, that means I'm going to add 1 to the exponent. So I'll have 3x to the 7th and then divide by the new exponent. This next part, I've got 3x squared, so I'll add 1 to the exponent, divide by the new exponent. Add 1 to the exponent, divide by the new exponent, add 1 to the invisible exponent. Remember, if there's an invisible exponent, secretly there's a 1 hiding there. So I'm going to add 1 to the exponent. I'll have 2x squared over 2. And then because I want all of my points, I'm going to include a plus c. One of the questions that I get asked a lot from students is either can I simplify or do I have to simplify? In terms of putting things into web work, usually you don't have to simplify. In fact, often web work would rather have you not simplify. But in this case, that would mean you're typing extra stuff that you don't need to type. 3 over 3, I don't need to type that. 3 divided by 3 is 1. I'm definitely going to simplify this term. Same with the 2x squared over 2. And once you have some practice with antiderivatives, you probably wouldn't even rate this. You'd look at the 3x squared and deal with the 3 in your head. Totally fine to write it out, but after some practice, you'll probably find that you're not doing that. Now, the 2 over 6, we could definitely reduce that fraction and say that that's 1/3. Totally fine. Also fine to leave it alone. But those instructions are secretly telling us to do 2 steps. Secretly, these instructions are saying, find the antiderivative, and then plug in what you were given to solve for C. When I look at problem 25, and it's super tiny on my screen, so I gotta like zoom in and stuff. Problem 25, I am looking at dr d theta is equal to cosine theta plus secant theta tangent theta. And we know that theta is between 0 and pi over 2. And we know that r of pi over 3 is equal to 4. So if I think about the 2 steps for solving that initial value problem, the first thing is, where's the thing that's a derivative so I can find the antiderivative? Then I'm going to use this extra information I was given to solve for C. So just starting here, notation-wise, that dr being on the top means that when I take the antiderivative, the function I'm finding is r. That theta on the bottom means theta is what's pretending to be x right now. So I'm going to treat theta as if it were an x. So I look at this and say, which function has a derivative that's equal to cosine? And that function is going to be sine. Then I come over here and I say, which function has a derivative of secant theta tangent theta? And that one is secant theta. So there's my antiderivative. And I'm going to remember to tack on that plus c. The next step here is to use the information we were given to solve for c. This isn't terribly interesting, other than this guarantees me that all of my trig functions are positive, because this tells me I'm in the first quadrant. There's also something else subtle here, which is secant theta is not defined at one of these endpoints. But the good news is these are not or equal to's. So it's okay. Now, does anyone know which of these endpoints secant theta would not be defined at? You can type it in the chat. 0 or pi over 2? I got guesses for both. Great. So let's talk about that. Because my sense is 3 of the 6 questions you were assigned to do here in the pre-rating assignment have trig. So I think that's an indication that trig is something that is going to be valued this quarter. So let's take a minute. Well, secant theta is the same as 1 over cosine. So in terms of a domain issue, we're going to be in trouble when cosine is equal to 0. And cosine of 0 radians is 1, but cosine of pi over 2 radians is 0. So this is the problem. So this would have been okay if I had a or equal to here, but it's a good thing we don't have an or equal to here, or we might have been in trouble. So back to here to finish off our question. Now I'm going to plug in the thing we know. So notation means this is telling me that theta is equal to pi over 3 and r is equal to 4. So I'm just going to plug those in. I'll have 4 is equal to sine of pi over 3 plus secant of pi over 3 plus c. Now, if you're like me, you sometimes occasionally forget your trig functions. You're not going to be able to use a calculator on exams, but for sure you can use a calculator on homework, or you can pull up a unit circle or go on YouTube and find the cool video about like how to use your tan something to know what all the values are. I'm not that cool, but Google it. People do such things. Personally, I always just end up drawing a triangle. So this is an equilateral triangle. All the sides are 2. So when I cut it in half, that's a 1. So I know my last side is square root of 3. And because it was an equilateral triangle, that's 60 degrees or pi over 3. So now I've got my triangle, and I'm just going to use SOHCAHTOA to read off what I need. So sine of pi over 3, I'm looking at the opposite side over the hypotenuse. So I'll be at square root of 3 over 2. And secant, my brain doesn't work very well in secant, but I know it's 1 over cosine. So if I find cosine, I'll just flip it. So for this triangle, cosine would be 1/2. So if I flip that, that would be 2 over 1. Now, if I were doing this and solving for C, I wouldn't do too much to simplify here. 2 over 1 is 2. We can do that in our heads. Go ahead and simplify that. So I can subtract the 2 from both sides, but I wouldn't do much more than that. I would say that C is equal to 2 minus the square root of 3 over 2. If you really wanted to get a common denominator with those fractions, you could, but nothing nice is going to happen to the square root of 3. You're kind of just going to be stuck with it anyway. So I wouldn't do any more than that to simplify. We don't have full points on this problem yet because we now need to stitch it back together. I need to take this answer that we got for C and plug it back in over here so that my final answer for the problem, I'll erase that C and stick in what we had, 2 minus square root of 3 over 2. So that becomes my final answer.